Yes, I'm a mess, but that's okay. Gotta do something fun today. Hello and welcome to another Solana tutorial. Today we're gonna do something fun. I have no idea if that's gonna be fun for you, but this is gonna be fun for me. Like, I've been looking forward to making this video. I don't know why I'm so excited about this, but today we are going to build our own transaction, low level. So what we're doing is we try to understand how a transaction is really serialized. We want to really understand the transaction header and all the fields that a transaction is made out of. That's, I don't know why, but for me, super exciting. And see, because here's the thing. You can develop on Solana without knowing this. You know, you have your transaction object, and then you somehow serialize that and send that to the RPC. You don't need to bother, right? The same way how you don't need to bother how an IP package is built. Like, what's the header there? That's lower level stuff that you're like, yeah, whatever. And what's the frame on the wire? We don't care. But somehow, I really do care. Just for my own understanding, and not because I ever want to build that myself. Except for now in this tutorial where I do it for fun to learn, but I don't have the ambition of writing my own code that can do that. There are libraries out there that do that. That's not why I'm doing this. And most likely you will not need to do that ever. But for me, it's about the understanding and the knowing what happens behind the scenes, because the more I understand, the better I can be in, making assumptions about stuff. And why would we want to understand the transaction, how it's serialized? Well, first of all, to understand really where those limits for, transaction length come in, and also what makes up the length of a transaction. You always hear, yeah, transactions have a size limit, but then what does it mean for you as a developer? You build your transaction and then it's either too big or it's not, but what makes a transaction big? That's what we're going to have a look at today. The individual things of the transaction that make up the serialized transaction that accounts for, the length of the transaction on the wire. We're going to have a look at Solana wire transactions. That's what they're called in the kit. And really, we're looking at how we can compile a transaction ourselves. That's the goal for today. And I'm super excited to do this. So yeah. Let's get started. I don't even know how I get started. I like this hoodie. Literally, I have no idea what I'm doing. I just have a rough idea of where I want to go. So the path is the goal here. It's the journey that is the learning experience, not the end goal. The end goal is like, yeah, great, we have that. We could have done that in one line of code with a kit, right? So that's, So where do we start? Should we first just do as we would normally send a transaction and go from there? That's probably easiest, such that you have something to compare to see where we are, what we even doing. Yeah, let's do that. So I will, because it rhymes, work with Gil. And then I'll do a new file with Gil. And basically I do the same example that we already had a look at in the video about Gil, where we do, a memo instruction, and also I want a transfer sol instruction because memos are boring. I don't want to do a memo. Let's do a transfer. I do one Lampert random receiver. If I don't log this, then I will lose it, but whatever. And source be my signer. That's not gonna work then, however, so let's do 1,000,000 Lamperts so that this is actually rent exempt. Compute unit limit. This screwed me last time, but 5k should be enough. If I want to be super efficient, I could do 450. That's exactly what it needs. If you don't know why, it doesn't matter. Go watch my compute budget video. Sign this transaction, then I send this transaction. Let's first test if that would actually work. Transaction simulation failed. This one has success, but then what's the error? Results in an account with insufficient funds for rent. Account 0. That's my fee payer. Account 0 is always my fee payer. Did I steal all the... Yeah, well, if I send... There we go. Okay, but now we should have enough. There we go. Hacker house. Simple. We send something to that account. Good, so that works. I mean, so far nothing new. But now let's analyze this signed transaction here and get a transaction codec. I never know if I want to encode or decode. I want to encode because I want the bytes, raw transaction bytes. That's what I'm interested in. There we go. So that's what this looks like. We have got a bunch of bytes starting with 1 and then a bunch of more bytes. And then we have something nice here, the 102, where I immediately see, well, that's probably the transaction header. And so this thing must be the signature. And I can see that when I look at that because I have the knowledge of how a transaction is laid out. If you look at that, especially the first time, you'll be like, I don't see anything. This is just bytes. I mean, there's a 3. Is that special? Oh, 127. What does that mean? You know, you have no idea unless you understand what those bytes really stand for. Because as with any serialization or deserialization, it's always what do the bytes represent? In storage, it's always just bytes. It's just ones and zeros, right? But it's a question of how you interpret them that makes up the actual data. So 1 byte could stand for a number, or it could stand for a part of a bigger number. I mean, this could be a number, or this could be a very big number. You know, and this here is not the only place in Solana development where you need to deal with that stuff. The way how Solana accounts are laid out, you are responsible for the serialization and deserialization. So you need to deal with that there as well, right? If we store an account, we say, okay, first 8 bytes are discriminator, then we have a U64, so that's another 8 bytes, then we have a vector of pub keys or whatever, so first there's the vector length and stuff. So you know, you're responsible for that, and then when you read the account, you just have the bytes, and then you need to deserialize that to get what you actually want. Here, we serialized that transaction, and that's the data that we then put in the actual IP packet that we send to the RPC. Well, actually, no. First, we encode that in base 64, pack that into HTTP, and the HTTP is then packed into IP, and that is then sent. But, you know, you get the idea. So those are the bytes that we send, and then the RPC will decode that again and make a transaction from it. It will decode and it will deserialize, because that's just a series of bytes. And then it will deserialize those bytes and do something with it. Same with the validator, it will forward it to the validator, and then it also looks like this. A transaction also looks like this, serialized, and the validators deserialize that transaction and then see if they can put it into a block. Yeah, that's how this works. And yeah, so we can understand what's actually happening here, how such a transaction is really represented, and then also prove that we understand by building it ourselves. That's what we're gonna do today. So yeah, let's get started really digging into what all those bytes actually mean. Should we start with the entire transaction outside in or inside out? Which way do we want to go? Should we start with an instruction and work our way out? Nah, I think it's best to start with the header. Let's first start with the message and we deal with the signatures later. Okay, there were graphics about this. Let me see if I can find them. Maybe it was in the cookbook. Version transactions. Yeah, that's it. We're gonna start with legacy transactions because it's the simpler one. And then in the end, we can have a look at what makes a version transaction. So for the beginning, let's pretend we're still in 2022 and there are only legacy transactions. Well, transactions, as they called them back then. Regular transactions. And you know, the legacy transactions is still probably, I have no data on that, but I would guess more than 50% of transactions are still legacy, although I have no idea, actually. But it's still being used, is my point. And the difference for you as a dev is also not really big, unless you're building the transactions manually like we're doing today. So yeah, a transaction consists of signatures and the message. So it's always signatures first and then the message. And you will see that more often, compact array. A compact array is actually really nice because somehow we need to say, well, how many signatures are there? Because it could be more than just one. So as with when we're providing a vector or a string, we need to say what's the length of the string and then give the string. Same here with those signatures. We need to say how many signatures there are and then the signatures. And you could say, well, I'm always just going to use 1 byte to indicate how many signatures there are going to be, because we know a signature has 64 bytes, so we can only fit so many signatures in one transaction anyway. So they could have defined that it's always the first byte indicating the amount of signatures. Then we're limited to at most 255 signatures. Hey, focus. I'm here. And that would be fine. For all intents and purposes, that would be fine. However, let's assume that for some reason transaction size would go up by 100x and suddenly we could do 300 signatures as well. Then it would have been a bad choice to define that the first byte indicates the number of signatures, because then we're limited by 255. However, that's where compact arrays come in. A compact array, like any array that you serialize, no, not true. Arrays where you know the size, you don't need to put the length up front. But compare it with a vector. Any vector that you serialize works like this. You say how long is it, and then you put the individual items. And in this example, each item has the same length. In this particular case, we're talking about signatures with 64 bytes each. But the interesting part here is how that length is encoded. And that length is encoded in a multi-byte encoding called compact U16. Now, what is that? Ooh, more graphics. Oh, that's where they have the images from. Maybe I want to go through this. Here we are in core concepts, transactions and instructions in official Solana docs. Yeah, that makes sense. Let's go there. Here we have the implementation of this short vec, short U16, serialize. There we see the code for it. Decodes an unsigned 16-bit integer, 1-to-1 encoded as follows. Now I also understand this better. So basically what's happening here is we use a special encoding for encoding a 16-bit integer. Usually how you would encode a 16-bit integer is by using 2 bytes, because 2 times 8 is 16. And with 2 bytes, you can easily, represent any number in a 16-bit integer. However, we want to be compact. And if we work with the assumption that most of the time our number is going to be less than or equal to 127, so it's less than 128, then we can say, okay, you know what? If I have such a small number, then I want my encoding to only take 1 byte. And we do that by the first bit of this byte indicating whether or not we need additional bytes. So in this case, if the first bit here is 0, then we know, okay, there's just 1 byte that encodes this 16-bit integer. And the encoding is pretty simple. We take the remaining bits and make it the number. We have those 7 bits that can represent 0 to 127. Only if we need a bigger number, we will say, hey, we set the 1. So this is not 0, this is 1. And then we immediately know, okay, we need now at least 2 bytes. And again, we do the same trick with the next byte. If it's a 0, then it's like, okay, the less significant bits from here plus those, they make up the number, the U16. But then we can still only get to 16k, and we said we want to encode a 16-bit integer. So we're missing 2 bits. Those are the ones that we lost here and here. So in the case where we need a bigger number than that, we will again set this to 1, and that indicates if both of the bytes start with a 1, then there are 3 bytes. So this is more than what we would use if we were encoding it with just always 2 bytes. And in this case, we just take the 2 bits from the 3rd byte, and those are then the remaining ones that can make up this entire 16-bit integer. Again, here we're wasting some bits because there will always be 0. But this will rarely be the case in our assumption that we have such big numbers. Most of the time we will be here or potentially here. Here it's still the same as if we had a regular 16-bit integer. But the advantage is if we have a small number, then we just need 1 byte. And in most cases, especially when we encode transaction stuff with this compact U16, then it will be just 1 byte. And I'm already going into details of the very specifics, but hey, we need to know this. Or we could just say, yeah, it's just 1 byte representing this because we never have more than 127 signatures, which, you know, fair enough. But that's not the full story. The full story is we could have up to 65,500 signatures. We could encode that if the transaction space could, you know, allow such a huge payload, which currently it doesn't. So it's pretty irrelevant. But they still said, hey, well, there's no point in saying, okay, it's never going to be more than 1 byte because it's also never going to be more than half a byte. So 127, well, half a byte in terms of 1 bit less, half in the numbers we can represent, not half in half the bits. Anyway, they said it's not going to be more than, or I imagine they said, it's not going to be more than 127 either. So we might as well say it's a compact U16 and then always just, you know, have be a 1 byte. Yeah. So much about short U16, this compact array format. Okay, that's pretty cool. This format is used to encode the lengths of account addresses and instructions in arrays, and also the number of signatures. So just that we understand that up front, what's a compact U16? Most likely it will just be 1 byte representing the length, but if that 1 byte is larger than 127, then we know, oh, it's more than 1 byte. It's probably 2 or maybe even 3. But at most, still we can have 65K because it is still a U16. Even though with 3 bytes, we could theoretically encode even more. And you know, you could play this indefinitely, add up to here until you make this a 1 and then you continue indefinitely to represent any integer. And you just add bytes as you need them. But no, in this case, it's really a fixed maximum 16-bit integer. That's why it ends here. Max encoding length is 3 bytes. Byte 3 continuous is an extra error. Yeah, cool. So let's continue here, actually. We said a transaction consists of signatures and the message. So we have this compact array plus the message. And then the interesting part is, what's the transaction message? What does it consist of? Starts with a header, then addresses, then a recent block hash, then instructions. That's the image for that. And that's for legacy transactions. That's what we want to build today, such a transaction message. And let's get started with the message header. We have had a look at this in previous videos, always a little bit, but let's dive in deep again so that for once, I really get those 3 things right, because it's always a bit confusing. Number of signatures, number of read-only signatures, number of writable signatures, read-only accounts, writable accounts. Which one was it? There's always a bit. So there are 3 things in the message header represented by 1 byte each. We have the number of required signatures, so there can never be more than 255 signatures, which kind of also limits the amount of, you know, signatures that we can actually provide. So, you know, maybe a 1 byte would have been enough, because otherwise we need to have a different message header, because those number of signatures obviously must correspond to the actual number of signatures, right? So wait, do we always have this byte double then? Because we have a compact array of the signatures where the first byte basically represents the number of signatures that we provide. And then this number of signatures, that's the number of signatures that the message requires. So theoretically what I could do is I provide more signatures than the message requires, but why would I do that? And also we wouldn't even know who they would be for. So I don't think that that's even allowed. Like, I don't think that it would even deserialize if I provide more. But hey, those are all things that we can have a look at when we really dive deep. Oh man, so many things to have a look at. But yeah, so point being, first byte is the number of required signatures. All of the signatures. That's for writable accounts and read-only accounts. If a read-only account needs to sign, also goes in there. And maybe we should also mention one more time, because you might not have heard that yet, the first signer is always the fee payer. That's how the fee payer is serialized. Because the object might have the fee payer and the address of it, but in order to save, transaction size, we don't encode who the fee payer is. No, we do that implicitly by always having the first signer be the fee payer. That's how that's done. That's how we save additional bytes. Because we could encode the entire account of it, but that would be a waste of 32 bytes. We could do the index, say fee payer is signer number X, but we can also say, well, there is at least one fee payer and there's always exactly one fee payer. So let's just say it's always the first one. That's smart. And the people who developed this are, you guessed it, smart. So the first byte of the header says how many signatures there are. Okay, so far so good. We can follow. Then it gets a bit confusing because the next one is the number of read-only signed accounts. So those are the number of signatures for not writable accounts. So those are total signatures and those are read-only signers. So this one will always be smaller than this one. If this one is bigger than this one, then it's like, what? This doesn't work. This doesn't deserialize. We could have alternatively said number of writable signers, and I'm not 100% sure why they encode the read-only signed accounts. Maybe in the implementation it makes sense that you have that number, but of course you can, once you have two of those three, you can compute the other one because it's a simple sum. All signatures are the read-only plus the writable ones, and then if you have two of them, you can calculate the third one. You could have also encoded number of writable signed accounts and number of read-only signed accounts. And then to get to the total required signatures, you would just need to build a sum. But here I understand how it's cleaner to have the total signatures because, for instance, the validators need to check all signatures, so they need to know how many signatures there are in total, and at that point they don't care about writable or not writable. So having that one byte represent the total amount of signatures makes perfect sense for me. And then the third thing that we have here is the number of read-only unsigned accounts. So we have read-only signed and we have read-only unsigned. And again, not 100% sure why they went for this versus saying how many total unsigned accounts there are. Oh, wait, I know why, because then you wouldn't get that information. So hold on. See, the message header is a substantial part of the transaction message. So I will go ahead and do a deep dive just on that message header. Yes, it's just 3 bytes, but I really want to understand why they picked it like that. And there's no real docs on that. The docs always just say that's the case. And even if I was talking to an answer dev, he was like, yeah, I guess I don't know. It's just been like that. There was one person who decided that, and then it's always been like that. But let's try and really understand what our choices here are. So we have this, we have this, we have this. Or let's do the same as in my transaction where we have 1, 0, 2. Now, if you see that header, do you know how many accounts there are in total? Because here are the things that we do not have in the header that we need to calculate. We have the number of total accounts. We have the number of writable signed accounts, writable unsigned accounts. The sum of those will be the number of writable accounts. And then we'll have the number of read-only accounts. And the sum of that will again be the total accounts. So those are all the things that we want to know. But basically what you really want to know is basically those 4, because if you have those 4, then you can calculate the rest, right? Because obviously this is this plus this, and this is this plus this. And guess what? Those we can also calculate from what we have. So the number of writable signed accounts is the total signatures, the total signed accounts, minus the ones that are only read-only. That's the number of writable signed accounts. And how can we get to the number of writable unsigned accounts? Well, guess what? We will need more information. We can actually not get that from just this, because we will need to know how many total accounts there are. So we're missing another thing that is not in the header, which is, again, number of total accounts, which in our case was 4. Spoiler alert, that's the next byte that comes there in the message. Let's say it's 4. Let's call this check, because this should then be the same as this, because this is literally the number of accounts minus all signed accounts. I have a mistake up here, sorry. I need to also say minus all of the signed accounts, because obviously all of the signed accounts are also not writable unsigned accounts. So having those 4 parts of the information in the transaction message, with 3 in the header and then 1 as part of what comes next, which is a compact array of all accounts. So the first byte of this, or actually possibly even the first 2 bytes of this, or maybe 3, would be the total number of accounts. We don't want to put that in the header if it needs to be in the compact array anyway, but it's directly after the header, it's fine. We just call this the header. So obviously you might have learned in middle school that if you need 4 pieces of information, you can't get that from 3 values. And we need 4 informations, which is this, 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 and this. So all the how many read-only signed, how many read-only unsigned, how many writable signed, and how many writable unsigned. With that, we can then work with all the accounts, because how is that actually serialized? What comes next, all of the accounts? That's actually serialized by the array begins with a compact U16 number indicating how many addresses it contains. Okay, we've talked about compact U16. The addresses are then ordered based on their privileges, which is determined by the message header. And this is the important part, this order. First, there are all the accounts that are writable signers. Then there are read-only signers. Then there are writable not signers. And then there are read-only not signers. So again, 4 pieces of information. For every account, we have 2 bits. Is it writable and is it a signer? And they're ordered by that bit as well, where the first bit is the signers. So first come all of the signers, then the not signers, and then within the signers, at first come writable and then read-only. First come writable and then read-only. So basically, those are the 4 pieces of information that we need. And again, as I said, we could have provided all those 4 pieces of information as individual bytes, and then we could, calculate the number of required signatures and the total accounts. But the thing is, we will still need to know the total number of accounts. So in this case, this will be this plus this plus this plus this. And then we also need to know the number of required signatures, because that's how many signatures we need to check. And that's this plus this. So both of the ones were assigned. And maybe you can already see how this part here is worse than this. I'm again providing 4 bytes, like I do here, I'm providing 4 bytes, but those 2 calculations are simpler than those 2 calculations. So that's one reason why providing those values is better than providing those. The other thing is, I immediately have this and this accessible. This I need for knowing how many accounts I need to deserialize, and this I need to know for how many signatures I need to check. And having those bytes directly totally makes sense. So that's why we provide those in the header and not the individual ones and then needing to build sums. That's stupid. So this is a really bad header. Let's stay with the same as we had before. We definitely want this and we definitely want this, but I can still not explain why you would put the read-only preferred over the writable signed. Maybe I would need to look at the implementation of it. But the important thing is, we know what's inside the header. It's the number of required total signatures, number of read-only signatures, so read-only account signatures, and then number of read-only accounts that do not require signatures. Could have also done writable and writable. I'm pretty sure there is a good reason why they did it like that, because as already mentioned, they're smart and there's probably a reason for it, but I can't tell. If I find out, I will tell you. We gotta make progress though. This is taking way too long. So those 3 things are in the header. Then, as we established, with the information from the header and the number of accounts in total, we can calculate all of those 4 values. And then for all of the accounts that are 32 bytes each, so it's just the public key that we encode here, 32 bytes public key, we can make the assignment of public key and role, so public key and is it a signer and is it writable, depending on where in the array it is, because it's ordered this way: first writable signers, then read-only signers, then writable non-signers, and then read-only non-signers. And we have the numbers for those. It's like this. And then right after that compact array comes a recent block hash. And if we are talking about a durable nonce, then it's the block hash stored in the durable nonce, or that hash stored in the durable nonce. I don't know what it's actually storing there, but that's a topic for a different video. Assuming that we have a block hash lifetime, it's just a block hash, and we know the size of it, it's 32 bytes, right? So it's another static 32 bytes, always 32 bytes. Every transaction needs that, so it's always exactly 32 bytes for the block hash. And after the block hash come the instructions. So we once again have an array, let me guess, a compact array of instructions. So there can be several instructions. So we will have a number indicating how many instructions there are. And then come the serialized instructions. So let's recap. What is an instruction made of? There are 3 things. Tell me. Yes, program ID. Yes, the accounts and the instruction data. Those are the 3 things that an instruction is made of. Program ID, accounts, instruction data. Program ID is going to be fairly simple because it's the 32 bytes of the public key of the program, right? So we would write the 32 bytes in the transaction here, right? No, obviously not. Why would we write 32 bytes if we already have all of the account public keys in a compact array up here? Obviously, we will just use an index to one of those accounts. You know, we have a length for this, and then we can index this array as you index an array with an index, a number representing the how manyth, which element you are trying to access, right? And in Solana, we need to provide all of the accounts, also the programs that we call. So the actual program ID will actually just be the index, and that's 1 byte. It's funny again that this is 1 byte, but the array itself is a compact array, so could theoretically have more accounts. But okay, we just can't access the accounts over 255 then. Not that you could provide more than 255 accounts because transaction size limits, but even if you theoretically could provide more accounts, you can only, the programs need to be within the first 255. Anyway, so we have 1 index for the program ID. Then come the accounts, and again, we will just reference which account we access. And here, once again, we're using a short vec. So once again, this representation, because we have a vector, so essentially an array with length, representing all of the accounts. And they have an order, because every instruction, you provide the accounts in an order. For instance, with a transfer, it's first the source, then the destination, I think. And so we can, reference the accounts we've already put in our array. And they need to be in a certain place in that array because some of them are writable, some of them are not, some of them are signers, some of them are not. But then we can use this index to point to anywhere in that array, thereby, again, taking any of the accounts from there. So we can start calling an instruction with a non-signer read-only account and then somewhere later have a writable signer. That's fine. And then the input data, well, guess what? That's again just a bunch of bytes. So we again just have a vector of U8s. And again, we will use this short vec encoding. Here we could theoretically have more than 255 bytes as instruction data. That's legit. So here having suddenly 2 or even 3 bytes of indicating the length of the instruction data could happen. That's the only space where it's actually practical, that we actually need more than 1 byte for representing the length. And for consistency, might as well have the same type everywhere because that makes stuff easier. if you have the same encodings everywhere. So yeah, that kind of makes sense. Besides, in accounts, we will also probably never get over the 227 accounts. So yeah, and those three things make up the instruction. And then we've got instruction after instruction. Here in this array, those instructions are not equal in length. So you need to deserialize an instruction to know where it ends. And then comes the next instruction. But it's always instruction after instruction until we reach the end of the compact array of instructions. And I guess after the instructions, that's it. That's everything for a legacy transaction. If you have a version transaction, there's also lookup tables. But for a legacy transaction, the message just contains the header, the accounts, the recent block hash, and the instructions. And then it's over. That's it. There is no byte indicating it's the end of the transaction message or it's the end of the transaction or whatever. No, because we always indicate length up front already. And we know how long the instructions are, and then it's just over. If there would be more bytes, then the deserialization would probably complain, hey, I didn't use all bytes for decoding this transaction. And then say something went wrong. I abort, I drop this transaction. Most likely, depending on implementation. Maybe they ignore it, but I'm pretty sure that's how it works. Okay, now that we are equipped with all this knowledge, can we build such a thing ourselves? Can we just create a transaction manually? Let's build ourselves a raw transaction. And we want to do a similar thing to what we did here, but we're going to make it a bit easier for us and not do the compute budget stuff. Let's just do one sol transfer, or even, you know what? Let's send an empty transaction. How about that? That's going to be the simplest. We're literally just going to use a fee pair. Let's just do the message. Okay, so if I want to create a raw transaction message, how am I going to do this? I think I'm just going to do this with a buffer. And we allocate, I don't know how many bytes we need, but at most we can have that many anyway, minus signatures. So first byte, number of signatures. I could build myself a header like signatures 1, read-only, signers 0, read-only, non-signers also 0 for now. And then I just write my header signatures, read-only signer, and read-only non-signers into my buffer. And then I have a offset of 3. So basically, so far, I've written the header. Great. What comes next? Oh, the compact array of accounts. So I will write the accounts, which, let's just take my fee pay. Those are all the accounts I will write. So I write a U8. Yes, note that we should write a compact U16, but I know that my accounts are less than 227, so I'll just write 1 byte. I'll make it easy for myself, even though this is a bit of cheating. And I write the accounts length at the offset and increase the offset for 1 byte. And then I encode my first account. So I could do a loop here. I'm like, for accounts of accounts, I write the account. So I encode the account, and then I get a buffer from this. Then I write this buffer. No, hold on. I copy this buffer to my transaction buffer at offset. Yes, and source start should be 0 and source end should be the end, so that's fine. And I know that that's 32, so offset plus 32. Should we already have a look at that? Let's see how that looks. Okay, so far so good. The header with 100, 1 account, that's the account. That looks quite promising compared to with GIL. If I load the same key pair. With GIL it looked like this. It had 2, 1, 2. 4 accounts, and then also 6, 76, 80, da 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 da. It's also what we have here, 6, 76, 80, da 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 da. So that's working, great. So we have the compact array of accounts. Then we need a recent block hash. I'm also let you give me a of type block hash. But what is it? Is it a string? What is it? How can I work with this? Character add, yeah, that sounds like a string. Ooh, but there's a block hash codec. Nice. So I will encode this block hash like I did with this. So I'm basically going to do the same, make a buffer from this, then copy it into the offset and add 32 bytes. Boom. block hash written to my buffer. And then it will look like this. I will have another 32 bytes with a block hash. Cool. What's next? Oh, all of the instructions. How about instructions B0? And we're gonna do the same fun thing as here. Write the instruction length and then each instruction. But for now, we don't need this because we don't have any instructions. And then we know that our actual offset now is also the length of the entire transaction, the serialized one. So could make a allocate that much and then copy it into that buffer again. Do you think that will just stop? I guess it will just stop if the final is smaller. Yep, looks good. So 69 bytes. Nice. So that's my message. My transaction message looks like this. I have one signer, one account, and it basically does nothing but fee pay. You think I can send that transaction? Well, for that, I will need to make it an actual transaction. I need to add the signatures. So, but the signing, I'm not going to implement that manually. I'm going to somehow get the signature for this message. Transaction. Let's see if that works. Because if that works, that's already going to be great. Wait, but that's the transaction. Wait, that takes the entire transaction. Wait, is there a get? Yeah, probably I want this. The compiled transaction message codec. I decode that and then I get what? A compiled transaction message. Compiled transaction message. And then this, the signer, sign transaction. I just need to get to the signature somehow. What if I just say add empty signatures to raw transaction? I will here define total signatures. I could read that from message bytes and later we might change that. And the transaction size from message bytes length plus 1 for the compact array, because we're not going to have more than 127 signatures, I tell you. And total signatures times 64 is 1 signature. So that's then the total transaction size. So let's allocate for that. And then write a uint8, the total signatures, and then, well, I leave it empty, so I'm not going to even write the signatures. I'll leave them 0 because we add empty signatures. So then I just copy the message bytes. We don't need to be efficient here and copy those to the transaction buffer. And then I return a new uint8 array. I could work with buffers all the time, but the kid likes uint8 arrays, so I'm going to make it a uint8 array. And then I'm going to pretend that this is my transaction, because it is. And then I'm going to proceed with this thing as if I could just sign it. Sign transaction message with signers. And for all of that to work, we need an actual transaction. Compile transaction is get transaction codec, decode this transaction, and that still doesn't work. Key pair is a crypto key pair, but you need an array. Ha! How about this? And then I get a hopefully signed transaction. Hopefully. We can once again have a look at the raw bytes of this thing after the signing, and then let's actually try and send this. We can't send the signed transaction because lifetime constraint. As fully signed transaction and transaction with block hash lifetime. Believe me, it's gonna be fine. Trust me, bro. This is not gonna work. Of course it's not gonna work. Cannot read property of undefined last valid block height. True, because I didn't set that. But this thing looks good. Look, I have one signature. Sha-la-la-la-la-la-la-la-la. That's the signature. And then here starts my message. So the signing actually worked. Hey, that's cool. Okay, maybe let's not do a trust me bro, but do an actual set transaction message lifetime using block hash. How about that? And we have the latest block hash up here, and we set it for the signed transaction. I mean, no, I kind of like my trust me bro. You just need the block hash for the confirming. Anyway, I don't want you to, you know what? How about I just RPC send transaction? I don't care for confirmations, just send it. Send. Not confirmed. YOLO. Oh shit. Invalid base 58 encoding. So this transaction clearly is not what we expect. Wait, you're talking about base 58. Invalid method parameter. Send transaction. I'm encoding it in base 64 because that's what you need. Then you complain about base 58. The server interprets it as base 58 then? Could that be? I'm just gonna log this. Hold on. I mean, yeah, that's what I have. But then the server complains that it expects base 58. Why do you expect base 58? Ah, because encoding base 58. Okay. See that the types here are not particularly encoding. Don't you have anything else? Yeah, base 64. Base 64. Okay. See, this is not my manual transaction creating that is the problem. It's working with the kit that is the problem. There we go. But hey, transaction sent. This is the transaction that's being sent. We have no idea if it landed or not, but we can check that. Look! We sent the transaction that we built ourselves. I mean, we did cheat a little bit with adding the signature. No, with creating the signature. Adding the signature we did. Nah, not even that. We added an empty signature and then we added it later. But I would say that's a success. At least we can build the message. And that's the interesting part anyway. We then still sign with a key pair like this. That's fair enough for me. And we first decompile the transaction such that we can actually work with it with a kit. The whole point of working on the pure pile transaction is being lost here again. But you know, whatever. If I could just get the signature somehow easily and then add it, I could easily do that because it would just be a signature bytes copy into the transaction buffer with offset 1 and then do that for each signature. You know, I could easily do that if I have the signatures, which I don't. Or, hold on, let's just use this to get the signature. Fine. I sign the transaction. From the signed transaction, I get the signature, get signature from transaction. And if I would have more signatures, then it would be an ordered map of address and signature bytes. Then I could do a function add signatures to a raw transaction, which would do the exact same thing. I get the signatures as a signature map, and then I would here say, oh, I would then need the addresses here. Nah, that's annoying. Let's just get one signature. Add signature to a raw transaction. Fine, singular signature. Shit, but then I need to decode that again. Yeah, that's a string again. Holy shit, that's annoying. If that was a uint8 array, I wouldn't have that problem. Buffer from signature copy into my transaction buffer with offset 1. That's how I would do it if I had the signature as a uint8 array. Let's see how I can get it out. I mean, this is just playing around with stuff. This is just TypeScript stuff. Signatures, add signer address. What are you? Your signature bytes or null? And I say you are signature bytes. Boom. Cool. I guess that will do. Let's see if I get with this signed transaction. Let's log that because that's again a uint8 array. This signed transaction, I then again need to decode here. But then we're actually just using the one that we did ourselves. So here we created all of this. This we created all of this ourselves. And then we put that in here again with that signature, get the signed transaction, and that signed transaction we again decode with a transaction codec that we can make the wire transaction from it. And basically we could also just, hold on, we have a buffer. If I don't want to, you know what? If I wouldn't want to rely on the kit for that at all, then instead of this, I could also just, you know, work with a buffer again. I should just always work with a buffer. I'm doing uint8 array to buffer to uint8 array, which is a bit useless. I should just always use buffers, but whatever. And then to string, make it base 64, and that should also be sufficient. Just that I then need to say S base 64 encoded wire transaction. Trust me, bro, it's that. Let's see if that works. Because then we don't rely on the kit at all, except for, you know, sending. But until this point, I don't want to implement the RPC stuff myself, and also don't want to implement the signing myself. So that's why I still rely on the kit. But otherwise, this is now directly from my bytes. I just make base 64 of it, and that I send to the RPC. Let's see. Would that work? Yes. Look, that's what I get. That's a base 64 encoded transaction. And did it land? Yes. That works. Like that I can send empty transactions. Whew, cool stuff. Okay, so I mean, okay, empty transactions is still a bit boring, admittedly. But before we add instructions, let's see what happens if I say my total signatures would be 2. Transaction failed to sanitize account offsets correctly. Oh yeah, because if I have 2, then, I mean, hold on. But it should still be okay because the second one is just zeros. That should be fine. But I don't even have 2 accounts. So that's my issue. What if I would add another account? Let's say I have a fee payer and I add the system program, whatever, it doesn't matter. Still failed to, here we have the system program. So if that doesn't match, then it just doesn't allow me to, what if I said I had 2 but if I say I have 2 signatures and I actually have 2 signatures, second one just being empty, then it says, oh, we're missing a signature. Yeah, that's fine. We can't sign for that. That's true. But it would already expect the signature for the system program because that's the next in the list of accounts. So that's working. Okay, what do? Let's add an instruction. Let's add a system program instruction with a transfer. So what we need to do, we don't add any signers, but we will need a non-signer, the system program. Actually, yeah, that's fine. And we will need still another account, but we don't need to say how many writable non-signer accounts we need. Maybe because writable are the most, maybe that's why, such that we can have more. Maybe the reason why we do it like this is just so we can have a lot of writable accounts, because with read-only signers as well as read-only non-signers, we're limited to 255 because, you know, that's the 1 byte here. But anyway, I don't think that's why they did. Anyway, I'm just thinking out loud. Moving on, we need to add an account, the system program, and the receiver. I use the same receiver as before. I'm going to use the 4D, and I need to put that before the system program because this one will be writable. So, you know, from the header, it takes the non-writable non-signers from the back and all the signers from the front. And from the signers, the read-only signers, which are 0, and then all the writable non-signers. So that's this one in the middle. Yeah, and my implementation here is good enough that I can just leave it like that. That's all I need to change for the accounts. Then for the instructions, let's actually build an instruction. I will have one instruction with a program ID index 2, because system program 012, and then the accounts being my fee payer as the sender and the receiver as the destination. And then the data, I know by heart that the transfer starts with 2 and system program I think has 8 bytes discriminators. So it's 8. And then I transfer 1 Lampert because I can. Or should we do something else? Should we do 255 Lamperts and 2, 3, 4, 5, 6, 7, 8, because that's a U64. And then I need to just put that data into my buffer. So transaction buffer, write U8, the instruction program index at offset and offset plus plus. Then both of that and that are vectors with compact. And since I know both of those are less than 127, I'm gonna again cheat and say it's just 1 byte. I'm gonna write the account's length for each account index of accounts. Gonna write that account index, and same for data. For each byte in the data, I'll write the byte. Simple. I could probably do that more efficiently, but who cares? And that should add an instruction to the system program. You think that's gonna work? I don't think that's gonna work. This is not gonna insufficient Lamberts. I think I have a, but hey, it already looks like the transaction actually compiled, or like could be decompiled and deserialized and read by the RPC, so it could simulate. But I think I have a 1 0 not enough, because that I don't like. What? Why do I need so many Lamberts? So hold on. Does the system program transfer not? Wait. Here where we did the transfer, can I see the raw data? Oh no, it's not 8, it's 4 by... Okay, yeah. 4 is still a lot, but it's... Okay, sorry. It's not 8, it's 4 bytes of discriminator, so that's what that should look like. Okay. But this gonna work now. Look! I can build my own transaction and send it. No, I cannot. Transaction sent. Okay, the RPC didn't complain about that, but it still didn't land. Okay, but let's see what the inspector tells us about this transaction. We have a valid signature for our raw key, and there is one system program instruction with that data. That should be fine. What happens if I simulate this? The simulation returns success. That's weird. I'm just gonna try it again. Because I'm not confirming, I don't actually know if it's, successful until I check here. Oh, this one is successful. So maybe it just got lost by the RPC, or my connection was bad or whatever. But yeah, it works. Look, I can send a legacy transaction, a call to the system program, and I could, now add other programs and other accounts, add an instruction to the compute budget program or whatever. And that's all just writing exercise. So I'm not going to do that. You can do that as homework if you want. Play around with it some more, how to build the transactions manually. But I'm happy with that. There's only one last thing that I want to look at. Look, 255 Lamberts. And that is version transactions. Just so we also looked at that. And then we call it, because it's been a long video. The main difference with transaction v0 is that the header has one more byte, and then we also have compact array address table lookups. And we could also analyze that, but I'm not going to. I'm going to send a version transaction without lookup tables. So why would you send a version transaction? Just to test, to know what we're doing there. In the message header, it mentioned that the required signatures and message version. So the first byte of the header, actually very similar to what we saw at the compact U16, does a similar thing. If the highest bit of this number is 1, then it doesn't say that we have more than 175 signatures, but it means that we have a version transaction. And the remaining 7 bits indicate the version of the transaction. So for instance, if we have 128, it means we have a version 0. And currently there are only version 0 transactions. And it also means, if the first bit is set, it also means that there's an additional bit in the message header. So we have 4 bytes. We have 4 bytes in the message header. And it doesn't say that here or here, really. Message header is unchanged from legacy? No. What? We also get an additional compact array of lookup tables at the end after... Oh, are they in the... No, where is that? We need to figure out where exactly that is. But I thought it's at the very end, which would make most sense for me. But that graphic makes me think something else. In my head, I would say it's part of the message header that gets another 4th byte. Let's just test it. If I were like, okay, instead of a raw transaction message legacy, I would now build a version transaction and I want the version 0, then I would write 128 plus version into the first byte. So this would indicate that it's a version 0. If I just add this 1 byte, then it will complain. Why? Attempt to sign a transaction with an address that is not a signer for it. Yeah, so there's clearly something offset now. And I think it's at the very end, after the instructions. That's how I remember it. If we use a version transaction, then we need to add this address lookup table stuff. But since that's also a compact array, I'm just gonna write a uint8 and say we have 0 lookup tables, 0 lookups, address table lookups, and be done with that. And I hope that that one additional 0 will fix my issue, but it doesn't. What am I doing wrong? Okay, can you, if I do it with Gil and I say version is 0, what does that look like? Can you show me? So I'm getting this right. It has a 128 and then the remaining header and 4. And I will need to see the rest of this. This doesn't look good. Fine, print me the entire bytes. Okay, I'll just scroll. So, we've got the signature, the header. I see the header here, okay. And then a bunch of zeros. That's probably the system program. And then a bunch of zeros. Oh God. Then a bunch of zeros. Oh God. Okay. What's the difference if I were to do it with legacy? Let's compare. I mean, yes, it's at the very end. At the very end, here we have 1, 2, 3, 4, 5. And here we have 1, 2, 3, 4, 5, 6 zeros. I'm pretty sure that at the very end come the lookup thingies with just 1 0. This one has 296. And this one should then have 297. Yeah, because one additional byte here and one additional 0 at the end. That should be it. So I think I'm doing this right, just that my signing doesn't work anymore. There's a lot of A's still. Oh, of course. There are a lot of A's. Now I get it. Hold on. Because at my adding the signature, I make the assumption that we have the old message header, which of course we don't. In this case, now I would need to access the second byte here. Okay, so really what I would need to do is if this byte is bigger than 127, then use that byte and otherwise use this one. That's what I would need to do. Oh, okay. That's my problem. Okay. I see. Okay. That's just printing what I have is like, okay, that makes sense. Okay, now, easy. Now it's easy. Look at that. We just have one signature. That's the message. There we go. That's easy. Isn't that easy? Sometimes it's fun finding those bugs. Yeah. And that's the problem if you build those things yourself. You work on assumptions and suddenly the assumptions don't hold anymore and everything breaks. So, of course, it makes more sense to use the kit and its functions for that. But it's nice to build it myself once. And now we also send a version transaction in version 0. Wow, amazing. All of that with building it all from scratch, manually writing it to a buffer, which, is certainly not nice code, obviously. Like, you don't want to do this for your project that you use in production. We're just doing this to learn. Well, I do this to learn and to prove that I really understood what's happening. Because it's one thing to read the docs and be like, yeah, that's how it works. But it's another thing to then actually build it yourself from scratch and see if it actually works the way that you think that it does. Because, I mean, knowing where I have to put this last byte for the lookup tables, I know that from a previous video, the docs didn't really tell me that. I had to basically know that. But yeah, anyway, so that's that. We can build transactions manually. I would say that's a success. Yes, we're done. I hope that you learned something. I really like playing around with this stuff. I really like digging into, well, how is the transaction actually serialized? And, by building it myself, I help myself understand. And I hope that I helped you also understand how this works behind the scenes, behind the compile transaction. That's what compile transaction does. And then we base 64 encode it and send that to the RPC. That's so cool. I hope you learned something. And, I'll be around teaching more stuff or giving you more pointers where you could look if you want to learn more about Solana development. Today's episode, transaction serialization. Because that keeps following me around and it's like an interesting topic that I wanted to deep dive in and spend 3.5 hours on, such that you can have a nice 1 hour video. Okay, Good. Well, in any case, thanks for watching. Here's other stuff that you can watch. Give this a like if you like that topic or just my face. I don't know. You don't need to tell me what you like if you like it. And you can also subscribe if you want to. And I will see you in the next video. Well, I don't see you, but you can see me. You know the deal. Till then, bye-bye. Woo! If you excuse me, I'm gonna join the Soluminati now.